Hi, my name is Owen Boxx, and this is the paper presentation for CS 487. So the paper I'm going to be presenting is a review of machine and deep learning techniques in epileptic seizure detection using physiological signals and sentiment analysis by Deba Prasad Dash, Manesh Kumar Kolkar, Chinmay Chakraborty, and Mohammed R. Khosravi. I'm sorry if I butchered those names. So we'll be going through an intro, what the problem is that the paper is addressing, prior work that kind of builds the foundation of the paper, some technical details that they get into, the results, and then the conclusion. So let's get into the intro. So what is a seizure and what is epilepsy? So a seizure is random uncontrolled bursts of electrical signals that occur in the brain. It manifests with different behaviors. So if you see, some people may shake, some people may just glaze over in their eyes where it seems like they're still there, but they're not. And they can generally be categorized into three categories: focal, generalized, and unknown onset. So focal is where the seizure begins at one point in the brain that can be identified, and the part of the brain that is affected by the seizure is where they would exhibit symptoms, such as like muscle control. That's when people would shake. Generalized means it occurs everywhere in the brain at the beginning, and unknown onset means we don't know where it starts. So it's kind of harder to predict those ones. Anyone is susceptible to have a seizure at any point in their life, but that doesn't mean that they have epilepsy, which is a seizure disorder. It's a neurological disorder, but more specific, it's a seizure disorder. You are considered to have epilepsy if you have a repeated seizure within 24 hours of another seizure. It affects an estimated 65 million people globally. The reason I chose this paper is actually because my dad, my whole life, has suffered from generalized epilepsy. Generalized or unknown, kind of have gotten different opinions, but and he's actually being considered for a new microchip to be inserted into his brain to detect oncoming seizures, which will be using a lot of this information that we'll be talking about today. So how do we detect seizures? So we are going to be talking about a lot of data, but a majority of the data used comes from electroencephalogram or an EEG. It's a medical test that measures the brain electrical activity. So it just detects electrical activity passing through the neurons in your brain. An EEG has a high temporal resolution, which basically means it takes a long time to record. It has a lot of stuff to cover, so it takes a while. There's two types of reading. There's intracranial and surface. So intracranial is when they would actually put sensors on your brain. Surface is when they would put sensors on your head around to get readings. And it is fundamental in generating the data used for detecting seizures. There's also some other things that we'll be talking about a little bit, which is an electrocardiogram or an ECG, which is essentially electrical activity, but instead of in your brain, it's in your heart. And is employed less frequently, but it still appears in some of them. So we'll talk about that. And then detection, we'll be taking these data and analyzing them. Historically, it's been done manually by doctors, and that's a problem. We'll talk about that in a few slides, but one of the reasons for the need to develop machine learning models and deep learning models for detection is because historically it's been done manually by experts in the field. So machine learning and deep learning applications in seizure detection. So there's potential for use in seizure detection based on electrical activity in the brain. So since we can record electrical activity in the brain, seizures are an abnormal amount of electrical activity in the brain. We're able to kind of create models to detect when a seizure is occurring and hopefully get better at predicting when those seizures will occur. So this paper discusses a few different machine learning and deep learning models that have been researched in the past. It's a review of a bunch of papers as well as implementing their own research on the long short-term memory network. So the models discussed include, I'll talk about all these later, an SVM classifier, ANN classifier, KNN classifier, RF classifier, HMM classifier, LDA classifier, CNN, P-1D, CNN, LSTM. LSTM is the long short-term memory network. I'll explain what those names are on a slide later in the presentation, but for now, I'm just going to go past them. So the paper performs an analysis on the effectiveness of time domain, frequency domain, and time frequency domain features. So essentially what factors are important. So machine learning and deep learning applications in seizure detection. So points of discussion within the paper included the different databases used, different ML techniques and DL techniques, machine learning, deep learning, and specifically feature detection or feature selection in a lot of those. So in a lot of machine learning techniques, they used handcrafted features versus in deep learning techniques, they talked about using the auto learning where it extracts its own features from the data. So in deep learning, it has an advantage because it's able to use an entire data set, while the data set for machine learning techniques can sometimes be scoped in, which isn't always a bad thing, but they talk about that a little bit. And then we'll talk about their own approach to the LSTM. So the problem. So there are a few factors that contribute to the main problem discussed in the paper. There's different data sets among different research papers, different feature choice among different research papers, and it takes time to manually analyze. So like when a doctor wants to manually analyze information given from an EEG for seizure detection, it takes a long time. They have to be an expert in what they're doing. So the main problem in the paper is there's a need to review and analyze the existing research done in the field of seizure detection using machine learning and deep learning models, and provide a direction for the future of research and application based on the analysis made. So prior work that is based on. So there's an application of deep learning and machine learning techniques that have shown good results in disease diagnosis. So there's a bunch of different papers that they go into, and I'm going to be going over some information from all of them. There's a lot of information, so I tried to pick the most important information that I gathered from the paper. So one example they gave, though, was that MobileNet V2 and LSTM in skin disease diagnosis showed great results. So they're trying to do also research in seizure detection. Many prior research papers' data, which included their models and data sets, the results of the said papers, and references to the said papers, which I'll apply at the end or show at the end. And then we'll talk about the databases. So as far as the databases go, there was three main ones. Three main types of databases, which was intracranial seizure EEG data, which, like I said, was when they actually touch your brain. Surface EEG data, which is when they put it on your side, and both of those are online, so they're online data sets. And then there's clinical EEG seizure data. So the intracranial, one example was the Bonn University online seizure database. It included 500 EEG signals of three categories: one where they were healthy, one where it was interseizure, and one while during a seizure. Interseizure is a period between when you're having a seizure and not. So it's like a weird in between. Then there is for the surface EEG seizure, CHB-MIT online seizure database, which included data from 24 subjects. And then there's clinical EEG seizure, which is clinical data. So All India Institute of Medical Science, or AIIMS, patent seizure EEG database. I'm saying these names because they might come up later in discussion during the PowerPoint, or the KU Leuven database. So this is just a diagram that was showed in the paper for the different kinds of databases that were utilized throughout all the different papers. And it has like the total number of seizures that actually occurred in each of the databases. Not necessarily, this number right here does not represent how much data there is, it's how much data for actual seizures that occurred. And let's see, let's go to the next one. So let's get into the technical details. So as far as feature selection goes, they discussed three main categories of features, which was time domain features, frequency domain features, time frequency domain features. There was a lot that they talked about, so I tried to grab what I thought was important, which includes types of features and some uses in certain cases. So for the time domain features, entropy was the biggest one. So it's extracted from an EEG signal and measures the uniformity of that signal. So types of entropy discussed included sample entropy, solace entropy, and fuzzy entropy. And the feature extraction came from graphs, graph nodes, and spatial graphs. So as far as frequency domain features, there were a couple spectral features. These are not all the ones that were talked about, but the flatness, the slope, the centroid, the roll-off, these are just some features that they talked about for domain features. The quadratic discriminant classifier, discrete Fourier transform, discrete Walsh, had a Mard transform, cross by spectrum, and cross by spectrum analysis was used to extract a lot of these features. As far as time frequency, it's a kind of like sounds like a combination of both. But the discrete wavelet transform was used to extract sub bands from signals. So essentially it's taking sub data from the signals itself. So it's, how do I explain this? You have the full signal and they only wanted portions of the signal. So stationary wavelet transform was used to extract the coefficients for intracranial EEG signals. And then joint instantaneous amplitudes and frequencies was another example of time frequency domain features. So these are some tables to show different features. So this one specifically is for time domain. So we have Sol's entropy, sample entropy, EMD, fuzzy entropy. This was provided in the paper, along with more information, which includes the classifier that was used in each case, the accuracy. So if we look at this with the ANN classifier and EMD higher order moments, we were getting 100% accuracy. But when we're using something like, let's get one that's close, this 99.16 was, or this 99 right here used a couple different features, and it used the LS or least square SVM classifier. So it's all, we'll talk about it later, but the accuracy is dependent on the model and the features. And this was another one. This one is for specifically frequency and time frequency, or time frequency domain features for intracranial EEG signals. And this is kind of the same thing. It has the model or classifier, the type of features that were utilized, and the accuracy. So the consensus when it came to feature selection was it's dependent on which model you're using and the structure. So it's separated into three types of approaches. There's the filter, the wrapper, and the hybrid approach. So the filter is fast, but capable of high and low accuracy. So they can't determine that it's going to be accurate. The wrapper is based on classifiers where they perform a forward and backward pass to then extract the features that they believe to be influential. And the hybrid is a combination of both filter and wrapping approaches. So these are some of the models discussed in the paper. I'm not going to be going into all of them because there's a lot of them, and I'm supposed to keep this to 5 minutes, but I'll quickly go through the main ones that were talked about throughout the paper, which was the support vector machine or SVM classifier, the artificial neural network or ANN classifier, the K nearest neighbor KNN classifier, random forest or RF classifier, which is essentially a bunch of trees. And then you take like the average across all those trees outputs, the hidden Markov model or HMM, the linear discriminant analysis LDA classifier, convolutional neural network CNN classifier, which we've talked about a lot in class, the pyramidal 1D CNN, or P-1D-CNN, which is essentially a different structure of a CNN, and the long short-term memory LSTM network, which is what they implemented in this paper and compared its results with the rest of the models. So really quick, I'll talk about some important points talked about from each of these. I tried to pick the important ones. There's a lot of data on it, but these were some instances of use of the different models. So for the SVM, it was used to solve the binary classification problem, and it finds an optimal way to separate the classes. It was also used with entropy as a feature, and it yielded really good results for accuracy in seizure detection. So it's important, there's seizure detection and there is seizure classification. So I'll be stating those. Seizure classification is classifying which kind of seizure. Seizure detection is detecting if there is a seizure. So it performed the worst actually when when the technique of optimum allocation sampling was used with it. And that was compared with the random forest classifier, I believe. And it was also used to extract sample entropy from data sets. It achieved a 96.84% accuracy in seizure detection when paired with the RBF kernel function. And the least square SVM performed well in seizure classification. Okay, so the ANN was used with oppositional crow search to speed up its convergence. It achieved good accuracy in seizure detection with higher moment features. And it was used along with time frequency analysis and achieved good accuracy in seizure and non-seizure classification. It did not perform well when provided image data, though. So it liked numbers, not images, which was interesting. So the CNN, the convolutional neural network, achieved a 99.1% accuracy for seizure detection when used as a P-1D-CNN, which was that pyramidal one-dimension 1D CNN. And it was used, that approach is essentially for refining. The P-1D-CNN is used to refine the approach of a normal CNN by segmenting the EEG signals into different parts. Essentially, it increased the sample size, allowing it when it trained to have a more robust model. It achieved good classification accuracy with 2 convolutional layers. They talked about a couple different convolutional layers where it was used. One was 13. From what I could tell, the 2 convolutional layers was the best performing. So a deep CNN achieved a 98.05% accuracy in seizure detection. With data from surface EEG signals, it achieved a 97.92% accuracy in seizure detection, and it achieved good results for intracranial EEG data as well. So the LSTM, so this is the one that they implemented, and the architecture is shown on the left. So it utilizes sequential data and iterations. So each data state or each state or iteration has a hidden state, which is the output state, and a cell state, which is information acquired from previous iterations. It can store and delete information based on the significance to the model, which is something that's special about this. It has the ability to essentially ignore or forget data that it doesn't want anymore. It can selectively read, write, and delete information as it trains itself. And it uses the TANH function for its activation function. Sentiment analysis. So sentiment analysis is analyzing alternative data values to the EEG values. Some examples are like stress, state of mind, voice recordings, or as we talked about, the ECG, which is like heart rate analysis for electrical activity within your heart. But the one I wanted to talk about that they really harped on in the paper was stress, because stress can actually lead to something called sudden unexpected death in epilepsy. So they used a decision tree, logistic regression, and random forest were used to detect stress. And the random forest classifier actually performed the best. And this can be used to not only improve the models, but also the treatment of the patient. So if you can lower the stress of your patient, make them feel better, they're a lot safer when it comes to having epilepsy, because they are not as high of a risk of that sudden death, sudden unexpected death in epilepsy. So the results. So the LSTM model achieved results from their findings that were on par with all the previous models. It held up. And it had the best accuracy came from combining ECG and EEG data for seizure detection across the board for all models that utilized it. So using both brain and heart data while analyzing created better results every single time. Both CNN and LSTM approaches achieved good results. They were the best. And then what they talked about was in future exploration is the LSTM with surface EEG data. So when they implemented it in the paper, they only used that should have been ECG data. But they used only EEG data, and they say for future, it's good to look into this model with ECG data. So they want to do the combination, because with the combination, they got the best results looking at previous models. And these diagrams are This is the same diagram for both, but this is just a comparison of the 3 best state-of-the-art methods for seizure detection. So in conclusion, increased research into machine learning models and deep learning models and their application in seizure detection leads to possible breakthroughs in seizure prediction. So a lot of this was talking about seizure detection. Essentially, can they detect if a seizure is happening? But there's a lot of this research that's going to be utilized in seizure prediction. Are we able to tell if a seizure is coming? And if we are, can we convey that to the person who is going to suffer from that seizure before it happens? So the need for evaluation among metrics beyond EEG signal data shows effective results in the accuracy and sensitivity of models. Basically, we need more to analyze more than just EEG data. It is the best data that we have, but it does not mean that we can't get more data and have more effective results. So the use of multiple databases is necessary to train the most robust and accurate models. Some of the models were used on different databases, whether separately or not. If you look at it, it is some of them used multiple databases, and the ones with multiple databases ended up having a higher accuracy a majority of the time. So the future of seizure detection / prediction lies in the research of multimodal approaches. Thank you. And here are all my references. I will quickly go through it, but they are also in the paper itself. Thank you.